You can share your screen, sir.
Okay, let me. Okay. So, all right, as I was saying, this is the last part of the last leg of the journey so far in Fsc112. And we'll be talking about organic chemistry. Now, without wasting too much time, we all know that organic chemistry is about the chemistry of carbon. And by now, you know that carbon is the sixth element on the periodic table. In other words, it means carbon has 6 protons. You know, the elements are grouped according to the number of protons that they have. So it means carbon has 6 protons in its nucleus. Invariably, that means neutral carbon as it is, we also have 6 electrons in its orbitals. But by now you know that the electrons, when you say electron in an orbital, is not like the proton in the atom of an, in the nucleus of an atom. All the protons are clustered together in the nucleus, whereas the electrons we know navigate around the nucleus. And the arrangement of the electron are based on certain rules. You will remember, or you should remember, your Hund's rule, your half-bow principle, and so on. All these are the rules that determines how electrons are shared into orbitals, or the arrangement of electrons in an orbital. In so doing, it means that for carbon, if we follow the spirit of those rules, we know that the first orbital, we have 2 electrons based on the 2n square root. So the first orbital, we have 2 electrons. The second orbital can have as many as 8 electrons. But for carbon, we say it only has 6 electrons. So that means if we put 2 in the first orbital, the remaining goes to the second orbital, which is 4. So that means the atomose shell of carbon has 4 electrons. And this is not too far-fetched if you recall that carbon is also, apart from the fact that it is having 6 protons, it is also placed in group 4. This is to tell you that it has 4 electrons in its atomose shell. So, but the question is, how does carbon utilize this arrangement in forming bonding? And it is interesting to know that carbon does this in so many ways. And in fact, that is why carbon has a unique place in chemistry, so much so that it has a branch of chemistry to itself that we call organic chemistry, because carbon has the ability to catenate. When you say catenation, it means carbon. And as a matter of fact, some other elements in group 4 also has this ability, though to a lesser extent. But carbon has this ability to catenate because it can link to one another and form long chain of carbon to carbon. And this can be done in different ways, therefore giving rise to limitless number of compounds that carbon can form. So organic chemistry in itself is the chemistry of compounds of carbon and hydrogen. And again, we can stretch that line a bit further because we have some organic compounds that also include other atoms apart from carbon and nitrogen. You can have organic compound with oxygen. You can have organic compound with nitrogen. We can have organic compound with sulfur, and so on, with chlorine. So Though basically most organic compounds we contain carbon and hydrogen, but it is not out of place to find other atoms of or other elements in those compounds. The compound, as the second line says, may also include oxygen, nitrogen, sulfur, and halogen, as the case may be. Carbon is the sixth element on the periodic table. I've said that today with an atomic number of 6. When you say an element has an atomic number of something, it means it has that number of proton. So atomic number tells you the number of proton. But we all know that for a neutral atom, the emphasis here is neutral atom, the number of proton is also equal more or less to the number of electron, but may not be equal to the number of neutron, which may differ, and that gives rise to when we have isotope. The carbon atom can covalently bond to other carbon atom, and this we call catenation. In other words, carbon can progressively bond to one another to form very long chain. This ability is not common to all elements on the periodic table. It is peculiar to elements in, or most peculiar to elements in group 4. Carbon can catenate. Silicon can also do a bit to some lesser extent. You will recall that silicon is just lower, the next is on the next period to carbon, that is period 3, while carbon is period 2, group 4. So catenation is peculiar to group 4 elements which carbon belong to. The ability to catenate decreases down the group, with carbon having the highest ability to catenate. So as I've said today, carbon can catenate, silicon can also catenate to a lesser extent. The next one is germanium, can also catenate a bit to some extent. So catenation decreases down the group. I can see someone raising his hand, David Echo. The only complaint I want to hear now is if you are not hearing me, because we just have 1 hour and we need to maximize the use. If that is not the case, then we can just quickly go on. If you have any question, you can type it up, post it on the chat, and before the last 5 minutes of the class, I'll go through it and give appropriate response. So how does carbon do this? I explained that the distribution of electron in the orbital of carbon is not like when you have what you have for proton that is just clumped up in the nucleus of an atom. The distribution of electron around any atom of any element is based on certain rules, some of which we already know. But if you can't remember, please go and revise Ohm's rule, Albauer principle. Also look up the 2n square rule of filling up electron into orbitals of an atom. That will make you recollect what I'm trying to say. So the location of bonding electron in carbon is best described by the quantum theory. If I am not assuming, you have talked about a little bit of this quantum chemistry with some of the lecturers that have been with you prior to now. So I won't delve too much on it. But the theory describes the most probable location of an electron at a specific energy level around the nucleus. The possible energy level are called orbitals, okay? And we have different types of orbitals. You have the sharp orbital, the principal orbital, the diffuse orbital, the fundamental orbital. This orbital we call S, P, D, and F orbitals. So you come across s orbital before. You've heard of p orbital. You have the of d orbital and f orbital. So so all these also plays important role in the chemistry of carbon. For example, if I'm or if I ask you to write the electronic configuration of carbon, electronic configuration of carbon, I'm sure that everybody in this class, we know that it is 1s2, 2p, 2p what? Okay, the class is not interactive. If you need to answer a question, you can just unmute yourself, and if possible, if not, we just go on. I'll try and answer my question myself. But the electronic configuration of carbon is 1s2, 2s2, 2p2, 1s2, 2s2, 2p2. Now, this is telling us that you have 2 electrons in the 1s orbital of carbon, which is the first orbital. Then you have 4 electrons in the second orbital. But the second orbital is also further divided into an s and a p orbital. Whereas the s can hold 2 electrons maximally, the p orbital can hold up to 6 electrons. So that's why you have the electron in the second orbital first going into the s orbital before the remaining 2 now goes into the p orbital. If I could scroll down a bit, let's yeah. Now, this is what I'm saying. The electronic configuration of carbon, as I just recalled, is 1s2, 2s2, 2p2. And if I can represent it this way, you have 2 electrons. You can see the arrows. And I mean, when 2 electrons are in a particular orbital, they assume different direction because one is spinning clockwise, the other is spinning anti-clockwise. So you have 2 electrons in the 1s orbital, 4 electrons in the second orbital, but the second orbital also has a 2s suborbital and 2p suborbital. Now, if you put 2 electrons in the 2s, it means you have 2 electrons left. But you also know that the p orbital is called a degenerate orbital. In other words, it is unlike the s orbital that is just one type. The p orbital is 3 types. So that means you have px, py, and pz that takes different directions of the Cartesian direction. So therefore, we only have 2 electrons left. So one of the electrons will go into the 2px, another goes into the 2py, and the 2pz is empty because there are no more electrons to distribute. We just have 6 electrons for carbon. And 1s has taken 2, 2s has taken 2, then px will take 1, py will take 1, and pz. And the question I always ask at this junction is that, why am I not putting the 2 electrons that is going into the p orbital all in the 2px orbital? Again, you remember your rule that when filling the degenerate orbital, or when electrons are going into the degenerate orbital, they go in singly first before pairing. Okay? So, but this is called the ground state of carbon. That is when carbon is at rest. and is not participating in any reaction. Okay, so if carbon is at rest and is not participating in reaction, the electronic configuration will be 1s2, 2s2, 2px1, 2py1, 2pz0. Okay, but carbon cannot remain in that state forever. There will always be reason for it to be excited in order to participate in bonding and so on and so forth. Therefore, to do this, something happens. Energy gotten from that excitation stage, we promote one of the the 2s electron. You can see my cursor moving on this 2s electron. One of the 2 electrons that was initially there here, one will now be promoted to the empty 2pz orbital. One of those electrons will be promoted to be empty 2pz orbital, such that the excited state of carbon, the electronic configuration will now be 1s2, 2s1, 2px1, 2py1, 2pz1. At this excited state, carbon is now ready to do its business, ready for bonding, chemical reaction, and so on and so forth. So again, note the differences or the subtle difference in the electronic configurations of ground state carbon and excited state carbon. But before we go on, let us quickly go a bit back to look at what we mean by, or the attribute of the s orbital and the p orbital, at least this stage. As you go far in your chemistry, you'll be able to grasp the attribute of the d and f and so on orbital. But for the s orbital, it has a spherical shape with the nucleus of the atom located in the center. So the s orbital, more or less, is just encapsulating the nucleus of the atom. The nucleus of the atom is just in the middle, and the s orbital is just all over, surrounding it. Then it is the lowest energy level electron can occupy in an orbital. In other words, the s orbital has an energy level that is low, and the lowest of the s orbital, and of course all orbital, is the 1s orbital. And that is why electron will always go into the 1s orbital first. When it is filled up, that is, if it now has 2 electrons, the electron will have no choice than to move, or any other additional electron will have no choice than to move to the next orbital. So each orbital can hold a maximum of 2 electrons. Each orbital can hold a maximum of 2 electrons. That is, each s orbital can hold a maximum of 2 electrons. Then we also talked about the p orbital. The p orbitals are the next energy orbital after the s. Okay, and like I said, the p orbital could further be divided into 3. We have the px, py, and pz, depending on the orientation of the orbital in space. PS, just think of your 3-dimensional orientation of the Cartesian curve. The one lying on the y-axis is the py, the one lying on the x-axis, the ps, are the one just in the middle, dissecting this x and y is the z-axis. So the 3 suborbitals are called degenerate orbitals and have a dumbbell shape. This is a dumbbell shape. Look at the shape here. Whereas the s orbital is spherical, but the p orbital is dumbbell, as if you are writing an enlarged 8. Okay? as if you are writing an enlarged H. So it is dumbbell in shape, and it is they are all degenerate orbitals, that is the three together. Therefore, you say the degeneracy of P is 3. You ask that what is the degeneracy of P orbital? It is 3. The degeneracy of D orbital is 5. The degeneracy of the F orbital is 7. So by implication, it means if the degeneracy of P orbital is 3 and it has 3 types of suborbital, therefore, saying that the degeneracy of D orbital is 5, it means that the D orbital also have 5 suborbital, and that is what it means. And any suborbital will always hold 2 electrons. It means that maximally the P orbital or any P orbital, whether it is the 2p or 3p or 4p, we always hold 6 electrons. Okay, the orientation in space is such that they are perpendicular to one another. In other words, the Px and Py orbital has 90 degrees between them. The Py and Pz orbital has 90 degrees between them, and vice versa. Each of the orbitals are perpendicular to one another, 90 degrees to one another. They are equivalent in shape and in distance from the nucleus of the atom. So back to our configuration of carbon. Therefore, when carbon goes into the excited state, that is what we call hybridization. In other words, there is like a mixing of the P and the X orbital, that is the 2s and the 2 orbital. Remember that one of the electrons of the 2s has been promoted to the vacant 2px orbital. So they are like equal in energy now. So they will now mix up. It's just like you mixing, saying you are mixing 1 part of fufu and 3 parts of gari together. So when you mix it up, whatever you come up with at the end of the day will have an element of your fufu, and we have an element of the EPA in it. So, but in carbon chemistry wise, the s orbital mixes up with the p orbital, and this mixing up produces what we call hybrid orbital. So prior to carbon going into bonding, the 4 equivalent orbitals now are mixed, and they form different hybrid orbitals. Now, if all the 4, that is the X and the 3p orbital, mix up together to form the hybrid orbital, we have what is called sp3 hybridization. Why is it sp3? If you go back here, it means you have S, just 1, P, 3, that is 3 P's. So sp3 hybridization. But if for a particular reason, one of the p orbitals says, look, gentlemen, I'm not taking part in your mixing up. I just want to remain unique as I am as a p orbital. Then it means that only 2 of the p orbital will mix up with the 1s orbital. The one that is not mixed up will remain, and will remain as what we call unhybridized orbital. But the other 3 will now mix up together to form what is called the sp2 hybridization. So a carbon atom that is having sp2 hybridization also has 1 orbital, 1 p orbital that is not hybridized. Okay, that 1 p orbital is not hybridized and it is staying on its own. Then the third scenario is that if just 1s and one P mixes together, then that means you have sp hybridization. It means the other two are saying, I'm not taking part in the hybridization, therefore leave us out. But this unhybridized orbital, whether in sp2 or sp hybridization, also has implication to the chemistry of carbon, because they are not participating in the hybridization, also bring another dimension to what chemistry can, to what carbon can do with itself when it goes into bonding, whether with another fellow carbon or even with another element. So again, let us take a look at what we just discussed. sp3 hybridization involves the mixing of one atomic s orbital and all the three p orbital to form four equivalent hybrid orbital, which is sp3 hybridized orbital. The four orbitals are spatially oriented towards the corner of a regular tetrahedron. This is a regular tetrahedron, okay? You can see the four hybrid orbitals. All these four hybrid orbitals contains one electron, okay? And the shape of the hybrid orbital is tetrahedral in shape. Note that the shape of the sp3 hybrid orbital is tetrahedral, and it has other attributes. For example, the angle between each of the hybrid orbital and the other is 109.3 degrees. 109.3 degree. Okay. Number one is that the shape is tetrahedral, and the angle between the hybrid orbital, this angle here, or if I take it here, this angle here is 109. Look at the angle, 109.3. Any of the orbital in relation to the other has an angle of 109.3 between them. So in methane, for example, okay, the question is, what does carbon now do with this orbital after you have hybridization and you have those four equivalent sp3 hybrid orbital? Now, remember that those hybrid orbitals, I told you that they have one electron, but that is not the end of the story. That means carbon now ready to go into formation of compound. So let's look at the simplest compound it can form. If each of those orbitals now overlap, now the overlap now is what is called horizontal overlap, because the overlap is like one end of the hybrid orbital overlapping with the other end while lying down. So end-to-end overlap, we call it. It is an end-to-end overlap. The end-to-end overlap, the hydrogen we bring is one electron and overlap the orbital containing one electron. That is the hybrid orbital, the sp3 hybrid orbital containing one electron. So that overlap will result in a bonding, and that bond that is formed is called a sigma bond. So therefore, remember that horizontal overlap or end-to-end overlap of two orbitals will give you a sigma bond. Okay? Then if the other orbitals too, if they now overlap with other hydrogen atom, the same horizontal overlap. So that means you have four hydrogen atom overlapping with each, each of the hydrogen atom will overlap with each of the hybrid orbitals. So you have four hydrogen atoms in total. And that will give you your first compound, which is CH4. Okay? each of these bonds has two electrons. Each of the bond has two electrons. One class, sir. Yes, sir. So each of the bond has two electrons, and therefore, altogether, you can see that the carbon that is now sp3 hybridized has fully formed a compound. Now, the nature of the bond is sp3 to s. sp3 to s, because this carbon here is sp3 carbon. The hydrogen that is coming is just bringing electron in the s orbital. The electron configuration of the hydrogen is 1s1. So it is just s orbital. So the hydrogen has formed a bond with the sp3 carbon. Therefore, the nature of the bond is sp3 to s. It is a single bond. The nature of the bond is sp3 to s. And all the other bonds here are all sp3 to s. Okay? All the bonds there are sp3 to s. So again, remember that the angle is 109.3. The shape of the hybrid orbital is tetrahedral, and that is why the shape of methane is also tetrahedral. And if eventually the carbon form a bond with another atom, the nature of the bond is sp3 to s bond. Generally, alkanes generally use sp3 hybridization to form bonds because alkanes are completely made up of single bonds. Okay, so they generally use sp3 hybridization. So let's look at the next type. sp2 hybridization. Remember, we informed ourselves that this involves the mixing of one of the s orbital and two of the p orbital to form the sp2 hybridization. The third p orbital, which is the pz orbital in the second energy level, which is the 2pz orbital, remains unhybridized and is perpendicularly oriented with the sp2 hybrid orbital that is formed. Okay, look at this. Whereas those in green are the sp2 hybrid orbital. The unhybridized one, which is purple, is just perpendicularly standing on its own. So the three sp2 orbitals lie in a plane at angles of the regular angles of a triangle. So it's just like having three corner pieces that when you connect together, we form a triangle. Okay? And the angle between them is 120. Unlike sp3, that is tetrahedral and has the angle of 109.3, the angle for sp2 is 120 to one another because there are just three of them. So, and they lie at the plane of a regular triangle. So that means if you divide it equally, you have 120 degrees to one another. So again, as we witness for sp3, sp2 can also go ahead to form bonding. Supposing you bring another carbon that is also sp2 hybridized, one of the lobes of the sp2 hybridized orbital can overlap with one another. You can see the overlap is also horizontal, end-to-end overlap. that forms a bond there. Put it as one of these bonds. That bond there is a sigma bond, is one of these bonds. The other ones can overlap with hydrogen. For example, this sp2 lobe of the sp2 hybridized carbon can overlap with one hydrogen, and you have this. This one overlap with another hydrogen, and you have this. And those are also end-to-end overlap to give you sigma bond. The same thing can repeat itself here. But look at this. This unhybridized orbital in one carbon can also overlap with another hybridized orbital in the second carbon. But this overlap is called a side-by-side overlap. You can see it is not end-to-end. They are overlapping. This is just to show that they are overlapping. You know, we are using 2 dimensions to explain a 3-dimension thing. But just take it as if this one is closer to this, and they are overlapping side by side. You call this lateral overlap, okay? And the lateral overlap will also produce a bond, because you know there is still one electron in the unhybridized 2p z orbital. So it will overlap with another one electron in the unhybridized 2p z orbital. That lateral overlap, in contrast to horizontal overlap, will give you what is called a pi bond. And that is the second bond between the 2 carbons. The first bond is a sigma bond, which is as a result of this overlap here. The second one is a lateral overlap, that is side by side, and that will give you a pi bond. And that is the genesis of double bond in organic compound. Okay, because one of the bond is a lateral overlap, is a horizontal overlap, that is between hybridized sp2 and sp2 carbon. The other bond is a lateral overlap, side-by-side overlap between the unhybridized 2pz in one carbon and unhybridized 2pz orbital in the other carbon. So between the 2 carbons, you now have 2 types of bonds. One is a sigma bond from horizontal overlap. The other is a pi bond from lateral overlap. And that is the genesis of double bond in organic chemistry. The shape of the sp2 hybridized carbon is trigonal. Okay, remember that. Now the shape of sp2 hybridized carbon is trigonal. This is in contrast to the shape that you have for sp3. And compound that you can have this sort of arrangement is ethene. Ethene is an alkene. It means that it has double bond in between. The nature of this double bond is sp2 to sp2. sp2 to sp2. So if I put a question mark here in the middle and I say, what is the nature of the bond? It is sp2 to sp2. The nature of this bond, this one here, which is similar to this one, which is similar to this and this, is sp2 to s. Contrast it to what you have in sp3. That one is sp3 to s, but here it is sp2 to s because this carbon is sp2 hybridized. For you to know the hybridization of a carbon, just look around the carbon. If the carbon just has only single bond around it, that carbon is sp3 hybridized carbon. If the carbon has double bond attached to it anywhere, it might be up, it might be down, it might be side. As long as double bond is linked to that carbon is sp2 hybridized carbon. So take note of that. Okay. Then lastly, we have the sp hybridization, where one of the X we mix up with one of the P to form the hybrid orbital. So in this case, you have two equivalent hybrid orbitals that is formed. That is the sp hybridization. The 2py and 2pz of suborbital, we say, I'm not participating in the bonding. So they will stay on their own and remain perpendicular to the hybridized sp orbitals. So supposing you have another hybridized sp orbital, you can also form a compound. So sp hybridization involves mixing of two s orbitals with one of the three 2p orbitals. The two hybrid orbital form lie on the same plane, and the angle between them is 180 degrees. So you know you have two hybridized sp orbitals now with one electron in their lobes. The two remaining unhybridized 2p orbital remains perpendicular to the hybridized orbital. When you hear perpendicular, it means that in relation to one another, it is 90 degrees. So in sp hybridization, you have two types of angles. You have 180 degrees angle, which is between the two hybridized orbitals, and 90 degrees, which is between one unhybridized orbital and one hybridized orbital. Okay. So if I give you the question, what is the angle between sp2 or sp hybridized orbital and 2px unhybridized orbital? You just put 90 degrees because it is perpendicular to it. But the angle between the hybridized orbital is 180 degrees, and the shape is linear. The shape of the hybridized orbital is linear. And we see this type of hybridized orbital in compound having triple bond. How did this happen? You know, you have two hybridized orbitals. If one of the lobe of one of the hybridized sp carbon overlap with the other one, they form a bond, which is a sigma bond here, because it is end-to-end overlap, sigma bond. Then one of the unhybridized orbital, say the two px of one carbon, we overlap laterally with the two ps of the other carbon, side by side. They form a bond there, which is what? A pi bond. The other unhybridized orbital, which is the 2pz orbital, we also overlap laterally with the other unhybridized orbital on the second carbon, and they form another bond, which is also a pi bond. So in a compound having triple bond between the two carbons, one of the bond is a sigma bond, the other two are pi bonds. And this is the origin of triple bond in organic compound. Okay, triple bond. One of the bond is a sigma bond. Two of the bonds are pi bond. Don't pay have you so those are the various types of hybridization that you can have in an organic compound. And that is the way carbon form different types of compound. Because in some compound, you see sp2 or sp hybridization. In some compound, you see the 3 hybridization. The compound we have carbon to carbon single bond. Somewhere it will have carbon to carbon double bond. And somewhere it will have carbon to carbon triple bond. So all the hybridization can be present in the compound. Okay. So in summary, I have this table. We have percentage p orbital, percentage s orbital. Okay. For sp hybridization, the percentage of the hybridized orbital for the p and s is 50-50 because it is just 1-1. One of the s mixed up with one of the p to form sp hybridization. So the percentage p character in sp hybridization is 50%, percentage s character is 50%. But when you come to sp2, you know, sp2, altogether, there are 3 orbitals here. One of the 3 is s orbital. 2 of the 3 are p orbital. So percentage p character will be 2/3 times 100, which will give you 6.7. Percentage s character will be 1/3 times 100. That will give you 33.3%. And for the sp3 hybridization, you have 4 orbitals there. 1 of the 4 is s, 3 of the 4 is p. Percentage p character is 3/4 times 100. Percentage s character is 1/4 times 100. Look at the relative overlapping power. Relative overlapping power means how well does those orbitals overlap with one another to form a bond. You can see that the overlapping power of sp3 is the highest, and that's why it forms a stronger bond than sp2 and sp3 overlap. So have these at the back of your mind. I mean, it's easy to remember when you know the numbers of orbitals in total, how many are p and how many are s. So we go a bit further to discuss bonding in organic chemistry. Bonding in organic chemistry are mainly covalent bonding. I won't go on to start explaining what covalent bonding is, but if I could just remind you, it is a bonding that you form by sharing of electrons. This sharing of electron could come in different ways. It could be 2 atoms participating in bonding. One is bringing 1 electron, the other is bringing 1 electron. They pull it together, they form a bond, as we've seen so far. There could be another way whereby one of the participating atoms is the one bringing the 2 electrons that is being shared. Then you say you have coordinate bonding or coordinate covalent bonding. But by and large, in organic chemistry, the bonding, the common bonding that's present is the covalent bonding, whereby you bring 1 electron, I bring 1 electron, then we share to fulfill the condition for forming a bond. But even in having covalent bonding, you could have different types of covalent bonding. There is what is called a pure covalent bonding, and we have what is called a partially ionic covalent bonding. If carbon is bonding with another carbon, you know they are both the same. Therefore, 5 minutes. You know they are both the same. Therefore, that sort of bonding can only lead to what we call a non-ionic or pure covalent bonding. because the two electrons that are being shared is just equidistant from the two atoms. It is just in the middle because they have the same electronegativity. But when you have carbon, for example, bonding with a much higher atom with a higher electronegativity, for example, chlorine. If chlorine is bringing one electron here and carbon is bringing one electron, the electronegativity of chlorine is higher than that of carbon. So the tendency is that the chlorine atom will have a higher capacity to attract the electron that is being shared to itself. Therefore, creating a situation whereby on an impression that the carbon has lost its electron to the chlorine. Though it has not lost it, unlike what we have in ionic bonding, whereby electrons are totally lost and gained. But for this sort of compound, we say it is partially ionic because the electron that even the carbon brought is closer to the chlorine. So the carbon here, we assume a partially positive charge, and the chlorine we assume a partially negative charge. In such a case, you say you have a partially ionic covalent bond or polar covalent bond. Polar in the sense that there's now like a charge separation, like charge separation between the carbon and the highly electronegative bonding. It is also present in organic compound, and it has implications to the compound because where you have this sort of polar covalent bonding, it affects the melting point and boiling point of the compound. Okay? It also affects the way the compound, the organic compound reacts, the chemistry of the compound, how it reacts with other compounds. Okay, so know that in organic compound you can have two types of covalent bonding, even though all organic compounds show covalency. The bonding in organic compound is covalent. If you look at the various bonding, you can have single bonding, you can have double bond, and you can have triple bond. But this covalent bonding could be of different kind. It could be pure covalent bond, it could be partial covalent bond. And this is where we round up the class for today. On Wednesday, we'll be looking at analysis of organic compound, the rudimentary analysis, quantitative determination of organic compound. What do you do when you want to determine the constituent of an organic compound, and so on and so forth. So I'll leave the next 3 minutes or so. If there is a question, you can send a message, chat, that I can. There's a question here. Please help me differentiate between lone pair and unpaired electron. Lone pair. Now, when you say, let me see whether I can. See whether I can find a suitable example. Okay, let me just describe it. And imagine if you have chlorine, or reminding the compound of HCl. In HCl, you have hydrogen bonded to chlorine. surrounding chlorine are 7 electrons, the neutral chlorine. 7 electrons. In such a way, if you arrange it, you have 3 pairs of the electron. 2, 2. 2, 2, we pair up. 2 electrons, 2 electrons. Then you have one that is unpaired. Okay? That unpaired one is a lone electron. Okay? It's a lone electron. It's not paired up. So a lone electron is an unpaired electron. 1 electron in an orbital is an unpaired electron. But a lone pair are 2 electrons that are not bonding. So you can have lone pair and bonding pair. Lone pair and bonding pair. Bonding pair are 2 electrons that you use to make a bond. For example, in here, these 2 electrons here, all these two electrons are bonding pair. Okay, but if you have chlorine, after chlorine would have used, for example, this HCl, or even this carbon to chlorine atom, this bond here is a bonding pair. But also surrounding chlorine that is not shown here are lone pairs. 2 electrons that are paired together, but that are not used for bonding. So you can have bonding pair electron, you can have lone pair electron, and you can have unpaired electron. Unpaired electron is just 1 electron. For example, this is an unpaired electron. All these are unpaired electron. This is a paired electron. Now, if this one goes ahead to form a union with another atom, it becomes bonding pair. Okay, so bonding pair is 2 electrons that has constituted a bond. Lone pair is a pair of electrons that is not used for bonding, but that is on the atom. Okay, is on the valence shell of an atom. It's called a lone pair. Then unpaired is just 1 electron that is waiting for an electron to bond with. What is the shape of the sp hybridized orbital? The shape of the sp hybridized orbital is linear. Linear, as if something is lying flat on a table. I mean, as if 2 things are lying flat on a table. And it's just like you and your friend lying on the floor, but not side by side, in such a way that your legs are touching one another. While you are facing north, your friend is facing south. So the angle between the 2 of you is 180 degrees. So it is linear. Okay. So I think those are the questions. Any other? Okay, let me see. I think the rest are just attendance. Okay, we call it a day. We will continue on Wednesday by His grace. if there are no other questions. Have a great day, sir. Coordinator, sir, permission to fall out.
Thank you very much, sir. We appreciate your time today, sir. And
Yes,
I will
sir.
also implore you to please put some questions together for me. I want to add it to the test, sir.
All right.
At least to deal with those that have refused to come for lectures. Please, I will appreciate if you can put questions together for me. Thank you, sir.
I'll do that, sir. Thank you,
Have
sir.
a great day, student. See you on Saturday for the test. There's going to be test on Saturday. Broadcast it. Thank you. Bye-bye, sir.